So, in terms of announcements, we are finishing chapter 8 today. Putting this up just to remind myself, we did efficiency already, right? Okay. So we talked about efficiency. I mean, there's only one more concept to discuss before we have officially ended chapter 8. After that, that will be everything that you need to do for your homework and quiz. And once we finish that up, you guys can have time to talk about any specific assignment or scheduling questions you have. If you don't have any pressing questions, then you can just break for the weekend after that point. So this is the final stretch of chapter 8. It's the last new thing that will be on the test that will be available to you to tail end next week. As a reminder, we will not have any in-person meetings on Tuesday. Use that day, A, to study, B, to vote. What I'm probably going to do is I will have office hours available remotely, kind of like we were doing during the last 2 weeks, where I'll be in a call that you'll have a link to. You come in if you have any questions as you're studying. I'll also probably maybe pre-record a video summarizing everything that will be on the test, so you can watch that instead of normal class time. The goal being to make it as flexible as possible, depending on your voting needs. So you don't have to be in a specific place at a specific time. But we will have normal classes on Thursday for review time before the test is available. Also, no labs at all next week. Remote or no digital lab, no in-person lab. Any questions, comments, concerns, or haikus before we continue today? Okay. If you have any questions, please ask at any time. Let's get to it and get through it so we don't get to our weekends. So, we have talked about the concept of thermal conduction before. Thermal energy can transfer from one object to another, and one of the simplest ways that can happen is through direct touch between two things. If I am touching this wall, my particles collide with it, thermal energy will go back and forth depending on those collisions. If you touch something and it feels cold to you, then thermal energy is leaving your body. If you touch something and it feels hot to you, then thermal energy will enter your body. Now, logic dictates that the hotter something is, the more heat you will feel, right? The higher something's temperature is, likely there's going to be more thermal energy rushing into your body and it will feel hotter. That's a completely logical thing to assume, and that is correct most of the time. But I want to bring to your attention, before we continue with this principle, something unique that you might not have noticed consciously before. Every item in this room, except probably the human beings, has been touching the same temperature air for a very long amount of time. You guys brought your own things in. They've been in different rooms, but the stuff that's been in this room overnight has been in the same room, in the same air, and all of the items that have been here the whole time have reached thermal equilibrium right now, which means they should be at the same temperature, correct? Now, the thing about your nervous system is you don't have a built-in thermostat. You can't touch something and your brain says, okay, that's 62 degrees Fahrenheit. All you can detect is heat leaving your body or entering your body. And the hotter something feels, the more heat enters your body in the same amount of time. The colder something feels, the more heat exits your body in the same amount of time. Your brain doesn't really care the temperature, it just cares how much heat is leaving or entering. Now, everything up here is at the same temperature. I promise you that. What I'd like, though, is at least one student, so that we have an eyewitness account that isn't just mine. Can I get one student to come up and touch, maybe just a pinky or a knuckle, this styrofoam object, and with a separate hand, this metal object. Now why don't you tell me if you feel anything different? You probably already guessed what's going to happen. This might not shock anybody. Okay, the metal feels colder. Not something anyone wouldn't have guessed, but why does it feel colder if they're at the same temperature? I promise you they are. They've been in here overnight sitting and equalizing, and yet one of them still feels colder than the other. Almost. Almost. You are getting to our main point here. Different materials have different rates of thermal conductivity, like how different materials have different specific heats. They may be at the same temperature, but they are both at a lower temperature than your body, because we are warm-blooded organisms, and except in deserts in the heat of the summer, our surroundings tend to be colder than what's going on inside of us. We're very warm inside as opposed to our outside. That means we have a lot of thermal energy to give to our environment. So those two objects are at the same temperature, but one is metal and one is styrofoam. Heat naturally flows through metal better than it does through styrofoam. So when you touch the two objects, the metal is a lot better at taking thermal energy away from you than the foam is. They're both colder than you, but one of them is going to feel colder, not because it's at a lower temperature, but because it is able to conduct more thermal energy out of you in the same amount of time. That is the math behind what we're going to look at, thermal conductivity. I'm going to roll it so that I can actually write on top of the next slide. So, this is a lot of new information. We're going to step through it one piece at a time. First, I want to draw your attention to this chart over here. This is a similar but distinct chart to the specific heat tables that are available in your notes. This is not specific heat. Specific heat is related but distinct. Every different material has a different coefficient of thermal conductivity. So it says up here, these are thermal conductivity constants in terms of joules per second per meter per degree Celsius. This tells us how each material has a tendency to allow thermal energy to pass through it. And just looking at each section on this table, we have items that are metallic, and at room temperature, they have relatively high thermal conductivities. It's units of several hundred. Compare that to the gases and the non-metals, whose thermal conductivities range anywhere from 2 to 0.02. Compared to the metals, barely any thermal energy transfers through these things. So even at the same temperature, they will feel different because, again, you're not sensing temperature, you're just sensing thermal energy passage. And what that means is, these materials, where thermal energy passes through them easily, are good conductors. It's the same word as electrical conductivity. They allow heat to pass through them. They are good at heat moving through them. Meanwhile, these down here are good insulators. They do not let heat pass through them very quickly, so they're good at keeping things on either side of a barrier at the same temperature. Notice, probably one of possibly the lowest number up here is actually air. Air is actually a really good thermal insulator, which is the reason why styrofoam is a very good thermal insulator, because this is mostly air. It's just foam beads with a lot of air inside of them. It's like the synthesized polystyrene equivalent of a marshmallow. This is mostly air, And thermal energy will not transfer very quickly through the air that makes it up, which is why it's a good thermal insulator. If you don't, an additional example with air specifically is double pane windows. Have you ever noticed that most windows tend to be two pieces of glass with a little gap in between them? That gap is full of air, which serves to insulate the window, to keep the temperature inside and the temperature outside separate. No thermal energy should cross through. The reason we would use air for that instead of any other kind of insulation is you can see through air. If you stuffed it with fiberglass, then it wouldn't be a very good window. So, these are good insulators. Thermal energy does not transfer through them quickly. This is why most buildings tend to be lined with something from this list. We don't have, I suppose this doesn't actually list most insulation on it, but notice that wood's thermal insulation is very low. A lot of buildings are made of wood. A lot of industrial buildings are made out of concrete, which is pretty low, at least compared to metal. A lot of walls are actually left with empty spaces so that there's air in them. That will help insulate them. And if you've never thought about it before, the native tribes in the north who build, at least stereotypically build igloos, ice is a pretty good insulator as compared to these materials. So you can keep the inside of your igloo a different temperature from the outside. That one on Magic School Buses again. So, what do we do with all of these constants? These are constants, they are known to you, you'll have access to this table, but what do we do with them? So, the rate at which thermal energy flows, thermal energy divided by time, the passage of thermal energy through an object, is power, because it's energy per unit time. So the rate of thermal conductivity is the same power that we've been using in previous chapters. So P is rate of thermal conductivity, but we can also call it thermal power. It's still energy over time. It's equal to the energy that transfers through the object divided by the time that it takes. But in addition, this formula down here looks at all of the variables affecting, all the variables about a specific object to tell you how fast thermal energy will transfer through that specific object. So this formula tells us that thermal power is equal to, the rate of conductivity is equal to K, and K is actually this table of constants. Your thermal conductivity constant for your material is K. So that's where the numbers from this table go. A, meanwhile, is the surface area of the object that thermal energy is passing through. I'm going to draw your attention to buildings for a lot of these examples, due to the fact that architects do have to take this into account, because if they don't, your building's going to be hot in the summer and cold in the winter, and everyone's going to want their money back. So, this is going to be a very poor representation of a wall. This wall is made out of some kind of material. It has some known depth, thickness. That is the length that the heat has to travel through to get to the other side. It also has some surface area. And if you were to take the width and the height of this wall and multiply them, that would tell you the area of the wall's surface. This matters because if this was a building and there was a blizzard going on outside, the bigger the wall, the more area it is for the cold wind to strike. The more area there is for thermal energy to come through the wall of the building. So the bigger something is, the more surface area it has, the faster thermal energy will tend to transfer through it because there's more space for it too. It's kind of like if you built the door to an auditorium much larger. The bigger the door is, the more people can pass through it every single second. So the area of the surface does matter. The bigger the area, the faster energy will transfer through. I already talked about this factor. The depth, the thickness of the wall also matters. Call it L for length, but I prefer to refer to it as how thick the material is because it literally is the variable of how far does the thermal energy have to travel to get from one side to the other. The A is in the numerator, so if A gets bigger, then P gets bigger. The more area there is, the more thermal energy will transfer every second. The bigger P is, the faster the thermal energy transfers. But the L is in the denominator, meaning if this number gets bigger, P will get smaller. The thicker the wall, the slower the thermal energy will transfer, because that's more distance it has to cover to get from one side to the other. That's one reason why, if you want to well insulate your buildings, you just make the walls thicker. And the last part is simply comparing the temperature on the hot side of the wall to the cold side of the wall. So let's just say that, I already said there's a blizzard going on, so let's say that it is 0 degrees Celsius outside, and we want to keep it at 25 degrees Celsius inside. Thermal energy is going to want to transfer from hot to cold, so it's going to make its way through the wall out to the blizzard. And the difference in temperature from one side to the other does affect the speed. If the hot side is a lot hotter than the cold side, there's going to be more thermal energy on this side that wants to get somewhere else. Thermal energy, like electricity, doesn't like to be clumped up together. It likes to spread out and be far apart and enter other objects. Since the particles that have the thermal energy are constantly bouncing off of one another, they're going to bounce away, and that energy is going to try to transfer away from where it already is. It wants to go from hot to cold. So the bigger this difference is, the faster it's going to try to get away. Like if you put a bunch of electrons in the same box, they don't want to be near each other, they're going to try to bounce away from each other. Meanwhile, if the temperature on the wall on either side was the same, if the temperature on either side was the same, this variable would just be 0. You wouldn't have any thermal energy flow. Because it doesn't need to flow if it's already the same temperature on both sides. So, those are all of the factors that determine the rate at which thermal energy will flow into or out of an object. Enjoying that thermometer? Be careful with lab equipment and all that. Any questions about any of this information? Okay. I'm really quickly going to rewrite the formula over here because we're going to work an example and it's not written on the next slide. One footnote worth noting. Because this is basically delta T, you can use Celsius here. Granted, Kelvin will always work, but as long as the formula is delta T, Celsius will work. Because the difference between Celsius temperatures is the same as the difference between Kelvin temperatures. Okay. So we're going to look at a specific example where you are trying to get thermal energy to transfer from one place to another. You are going to try to boil or increase the temperature of the liquid inside of a pot. And most cooking pots are made out of metal. They tend to be round, which means that the surface area of the bottom of this particular pot is going to be a circle, and the material tends to be only so thick. And since the whole point of a stovetop pot is you want thermal energy to get from the hot side to the inside, you don't really want the bottom of your pot to be super thick, because if it was, thermal energy wouldn't transfer as quickly. But at the same time, it needs to be thick enough and sturdy enough to withstand all of the cooking you're about to do. So, you've got to strike a balance there. We are looking at a specific copper pot, so we already know what it's made of. That means in a second, we need to look up the thermal conductivity constant of copper. We are trying to heat up ice-cold water. If the inside is full of ice-cold water, then that means we know its starting temperature is going to be 0 Celsius, TC, 0 Celsius. We know that the hot side, the stove eye is the hot side. The actual heating element is commonly called a stove eye. You haven't heard that term before. So the actual hot element that the pot is sitting on top of is 300 degrees Celsius. So conveniently, the delta T is going to just be 300. That's nice and easy to calculate. We are also told that the bottom of the pot is 2 millimeters thick, and it's a round pot. It has a diameter of 12 centimeters. So, with all the information that we're given, what do we need to do to be able to calculate the thermal power, the rate where thermal energy passes through this pot? All right, we need the surface area. The bottom is a circle. We know its diameter, so we just need to look up how to find the area of a circle, which is pi r squared. So that's the diameter. The diameter is radius times 2. So we need to turn our diameter into radius, then use it to find area. And I will never deny you, I will always tell you this formula, because I usually forget most of these geometric formulas involving circles. I can't even remember most of my actual physics formulas most of the time, because I'm so used to having them in a reference book. So it's one reason why I will never hide a formula from you, because it's never hidden from me. I certainly couldn't do my job. Okay. So this number is our diameter, which means our radius is going to be 6 centimeters. Radius is always half of diameter. So, what should the area of the pot be? The surface area of the bottom of the pot.
113.1.
One more time.
113.01.
Okay. So, when you plug in the number 6 right here, you'll get pi times 6 squared, and that would give you 113 point, you can round that off to 1. But we plugged in centimeters into that, so that's going to give us the area in centimeters squared. Is that the standard unit for area that we would want to use in our formula? No. So we need to convert that to meters squared. Say it again?
1.13.
Almost. Almost. Say it again?
0.1,
Almost again.
0.01?
Yes. I will show how you get there. But just go ahead and put it up on the board. So that is the surface area. And to show the conversion, we started with centimeters squared, and it is squared, meaning that this is basically centimeters times centimeters. So we need to convert centimeters to meters once. And if we do that, only do it once, that would give us 1.13, but again, that would not be meters squared. It would be centimeters times meters. So you gotta do it twice. So ultimately, you would move the decimal place 4 times to the left. It's not actually a very large pot, it's only a foot across. But that gave us our area, and we know its thickness in millimeters. So what else do we need before we can continue and find P?
The constant.
Very good. So we're just going to tap back, and we're just going to look on that table for value for copper. Copper's a metal, so we'll look up here. Thermal conductivity for copper in joules per second per meter degree Celsius, just making sure our units match up, is 397. So let's write that down. I know this value has very strange units. They are only really important to check to make sure that everything cancels correctly. So I'm not too bothered by you remembering this unit. Just look at the table to make sure that it's normal joules, normal seconds, normal meters, and normal degree Celsius, or degree Kelvin. Actually, no, there is no degrees Kelvin. It's just Kelvin. So, with that done, I think that's everything we need. So let's start plugging things into our formula. We're solving for thermal power. It's equal to K, 397, and the area, 0.01111, times our temperature differential. It's 300 on the hot side, 0 on the cold side, and the pot thickness. It's listed as 2 millimeters. So what number should we write? Say it one more time, sorry.
0.02.
Almost. Centi, you divide by 100. Milli, you divide by 1,000. So it's going to end up being 0.002. I should include a metric conversion table in the form of sheets. But that is every number of the formula. We can now solve for P. Make sure you plug everything carefully into your calculator one step at a time. There. I'm going to go digging board today. What's everyone got? Very good. And what is the unit used previously. Very good. Watts. And just as a refresher, 1 watt is equal to 1 joule per second. So every single second, this number of joules worth of energy is transferring through your body. Which is a lot. That would, for a very small amount of water, that would heat it up pretty quickly. But that is the thermal power. That is the rate at which the thermal energy is going to transfer through this particular object. This sort of thing is important to architects because you need to insulate your building, or whoever you build it for is going to want their money back. It also matters if you are building any device or appliance that has to do with thermal energy or the ocean of thermal energy. What I mean by that is basically a refrigerator, because you want the inside of the refrigerator cold and the outside to be warm. So you have to, like, instead of the wall of the building, imagine this is the wall of the fridge. You want to make sure that the walls are thick enough and well lined enough to keep thermal energy from entering it too quickly and spoiling your food. Which was actually my research project to get my physics degree at DC, because I was working with Dr. Odekor on a project involving the efficiency of appliances, and I was specifically given the refrigerator section. So I did fridge research to get my degree. My friends never let me live that down. And what that number over there can tell you is, like, say we were looking at the wall of a house, and we got a similar power through the wall of a house. Since that means joules per second, energy per second, and you wanted to keep the inside of your house at the same temperature, you would need to produce through your heater that many joules every single second to counteract the thermal energy leaking through your walls. So again, engineers, architects would need to know that number so that they know what the heater needs to be capable of to keep the building at the right temperature. Any questions? Okay. With that, that's the end of the information in Chapter 8. That's everything involving heat and thermodynamics that you are going to need to know. And that is the last piece of new information that will potentially be on next week's second section test. So, now if you have any questions about anything that will be on the test, or the test itself, or the schedule of the coming weeks, speak now. You don't have to forever hold your peace, but have a chance to speak now. Okay. With that done, Chapter 8 is done, so unless you want to stick around and review, you are free to go. And I do hope you all have a wonderful weekend. We'll review for the test next week. Instructions will be given for how sort of the virtual format of just Tuesday will work. And work on your chapter assignments. It helps all of us if you aren't